All right, so the winding number before is the number of times a closed curve winds around 0. If this thing here is 0, then given winding anticlockwise, so I claim the winding number of gamma is given by this. 1 over 2 pi I, the integral around gamma of 1 over z dz. Okay, so I'm going to show this claim, and the first thing to notice is the following. So proof. First, recall the complex log. Which we define to be this. So log to the base e is just natural log. We just write log to the base e to differentiate it from complex log. So it's natural log of z bar plus I arg. And for the argument, I'm going to take the principal argument. So the principal argument, recall, belongs to pi to minus pi, like this. So we measure the angle like this. This is pi, and like this is minus pi. Right? So for every z, there's a unique number such that this is true, right? So z is equal to e to the I arg of z. This is the principal argument. Yeah? And as you know, this obviously has a discontinuity as we try and cross across the negative real numbers. Yeah? But this, nevertheless, apart from this problem, is a perfectly well-defined holomorphic function, and we can define a different branch which doesn't have this particular discontinuity on this side. So practically speaking, the discontinuity of log usually is not a problem, but it is an essential feature in what we're about to do. So log is the inverse of e to the z. So you have e to the log of z equals z, right? So then if we differentiate it, then we have e by dz of log of z, e to the log of z is just equal to 1, right? And e to the log of z is just z itself, right? So d by dz of log of z is 1 over z. Yeah, just like on the real line, except now it's true as a complex number. So this is what we're going to do. We are going to break this curve up into pieces, and I'm going to make life simpler. I'm just going to make this thing loop around just 2 times. So let me erase some features here. So I'm going to show you that if we loop around 2 times, we're going to get exactly the right thing, and the argument works in general. But we're just going to not write out all the details because it looks somewhat lengthy. Okay, so this is a closed curve. It loops around 2 times. Yeah, and we can start parameterizing it from any point, right? So let's put the put the negative real numbers here, okay? And let's start our parameterization just underneath here, and let's go around like this. Actually, let me change colors. So this is the negative real numbers here, so this here is 0. And let me make this in blue, so we're going around like this, like this, like this, like this, like this, like this. So let this thing be the first part of our path. Okay, and I'm going to call that one gamma 1. I'm going to stop just a little bit short of the negative real numbers, and I'm going to restart just a little bit underneath it. And I'm going to take this path here, which goes around like this, and does the second loop, and I'm going to call that gamma 2. So that's gamma 2. Better if I had a different color. Let me make a different color. So this is gamma 2 here. And just to stay in the place where it's holomorphic, I'm avoiding the negative real numbers. So I'm just stopping short. So strictly speaking, gamma is not decomposed into gamma 1 and gamma 2. There's also these little bits here that I'm just not going to talk about. So I'm just going to like, there's a little bit here and a little bit here. I'm just going to, well, I'm going to talk about it, but I'm just not going to, I'm going to consider those as errors. So that's the first error, E1 and E2. And they're as small as you like. They're tiny, tiny little bits, just a bit of the path that actually goes through the negative real numbers. So what we have is the decomposition of, so gamma equals gamma 1, union gamma 2, and then these tiny errors. And then E1, and then E2. Okay? And we are going to think about this integral right here. So this integral, so integral of our guy gamma y over z is the sum of gamma 1 plus gamma 2 plus these very small errors. Oops. And I don't care about them because 1 over z is bounded because we are some definite distance away from 0. So on this little error here, we are some definite distance away from 0. I'm just going to make the length of this little part as small as I like to make this thing as small as I like. And the same thing here. So these guys, I claim we can just forget about because the function we're integrating is bounded on these little paths, and I can make the length of the path as small as we like. Yeah? So they're not really an issue. So all I really have to think about is gamma 1 and gamma 2. Yeah? So we look at gamma 1. Gamma 1 started here, and it ended here. Yeah? Started here, and it ended here. And let's call the part, the complex number where it starts, a mess. Let's call the complex number where it starts S1, and where it ends is S2. And then gamma 2 starts somewhere here. Let's start where it starts is S3, and where it ends is S4 over here. Right? And S2 and S3 are very close together, and S4 and S1 are very close together. Yeah? And then we can parameterize gamma 1 any way we like, right? But we have the fundamental theorem of calculus in the complex plane. Because for gamma 1, in this region, we have a perfectly nice holomorphic function in an open set. Yeah? Yeah? So we have the antiderivative, right? The antiderivative of this guy is complex log. Yeah? So I know that gamma 1 integral over gamma 1 of 1 over z dz is complex log of the endpoint, which is S2 minus complex log of the start point. And what is this thing? This is log to the base e of absolute value of S1 plus, oops, of S2, sorry, plus the argument of S2 minus log to the base e of the absolute value of S1 plus the argument of S1. That's just the definition of complex log. Yeah? Cool. And for this integral, gamma 2, 1 over z, dz, I have the same kind of thing. Where do I start? I start at S3 and I end at S4. Yeah? So I have that this thing is complex log of S4 minus complex log of S3. And what's that? That is log to the base e of the absolute value of S4 plus the argument, oops, absolute value, plus the argument of S4 minus log to the base e of the absolute value of S3. So I should put a bracket around here. Plus argument of S3. Yeah. Yes, sorry. Yeah, we argument it's got I here. Indeed. Where did I put the original definition? There we go. There we go. Good. All right, cool. So all we have to do is to add this guy to this guy. Yeah. And that, with a tiny error, will give us actually what the entire thing is. Yeah? Yeah? And if we do add these expressions, well, what happens? Well, I claim that the real parts are all going to vanish. So let's see why. Well, vanish with very small errors. So if we add this to this, well, what do we know? We know that the absolute value of S4 is very close to the absolute value of S1. Yeah? So this S4 with this minus S1, these guys will cancel. Yeah, so we're adding these two things. I'm out of space. Maybe I'll put it somewhere though. Yeah, let me put it somewhere. I just got new pens, but they're harder to erase for my fingers. So, integral of gamma 1 over z dz plus the integral over gamma 2, 1 over z dz. We are going to have that, again, this guy basically cancels with this guy. There's a tiny error, but we don't care about it. Yeah? And if we look at, let's look at the positive term. If we look at log of S2, log of the absolute value of S2, that's this thing. And that's incredibly close to the absolute value of log of S3, because S2 and S3 are incredibly close together. Yeah? So this guy will cancel with this guy. Cancel in the sense that there's a tiny error. Yeah? So we don't have any real parts except for some very, very small thing, depending on the width of these little things we've jumped over that we don't care about. Yeah? Give me a thumbs up if you're with me. All right, super. So we have just the imaginary parts to think about. Yeah? So we have the I times the argument of S4 plus I, let's put the positive terms, plus the argument of S2 minus I times the argument of S3 minus I times the argument of S1. Right? And then plus or minus very small real error. Okay, but if we look at what these arguments are, so what's the argument of S4? S4, the argument is very close to pi. Yeah? Argument of S2 is very close to pi. Yeah? The argument of S3, we're going around this way, it's very close to minus pi, and the argument of S1, going around this way, is very close to minus pi. Yeah? So this thing is actually equal to 4i times pi plus or minus very small error. So in particular, 1 over 2 pi I, the integral of 1 over z dz, which is very close to this quantity, is basically just 2. And as we let these little gaps get smaller and smaller and smaller, as we have the right to do, then these errors go to 0. Yeah, because all we need is just to have these curves that we've defined be inside an open holomorphic, inside an open set where the function's holomorphic. Yeah, cool. So this shows that breaking up the curve in this way, using the fact that 1 over z is the derivative of log of z, this gives us that this is the correct formula. And this can be generalized to any number of loops just by cutting up into more pieces, as you can imagine. Yeah? Cool. So we do believe this. This thing does indeed give us the winding number. Yeah?